All right, so this week we're also going to start with the beginning of chapter 5 on learning how to standardize our analytical methods. So you'll be using this technique in the lab this week. So anytime that you're analyzing for an analyte, you need to have a standard that's going to help you determine the concentration of that analyte in your sample matrix. So this can be a primary or a secondary standard. So a primary standard is a reagent that we can use to dispense an accurately known amount of an analyte. A primary standard has to have a known stoichiometry or a known purity or assay, and it must be stable during long-term storage. So a lot of compounds, right, will hydrate and they'll take on water molecules over time. So it's very difficult to actually establish the complete degree of hydration even after drying a sample. So if you have a hydrated reagent, this usually cannot be used as a primary standard. So there also are secondary standards. So any reagent that does not meet the criteria of a primary standard is considered a secondary standard. So the concentration of a secondary standard is determined relative to a primary standard. And then you can use that secondary standard in the place of a primary standard. Sodium hydroxide is a good example of a secondary standard. So when you have commercially available sodium hydroxide, it typically contains impurities such as sodium chloride, sodium carbonate, or sodium sulfate. And it also readily absorbs water from the atmosphere. So to determine the concentration of sodium hydroxide in a solution, you have to titrate it back against a primary standard. So you can use a weak acid such as potassium hydrogen phthalate for this purpose. And we'll do preparation of a standard like this later in the term. You'll make a 1 molar solution of hydrochloric acid, and you'll need to use that as a secondary standard. So you'll need to confirm the concentration of hydrochloric acid in that sample by doing titration against a weak base. So preparing standards often requires additional reagents that are not primary standards or secondary standards. So sometimes you'll need a suitable solvent or other reagent that's needed to adjust the standards matrix. So these solvents and reagents are potential sources of additional analyte as well. So if you don't account for this, it may produce what's known as a determinant error in the standardization. So when you're preparing a standard solution, if you're working with a large range of concentrations, particularly a range that extends over 3 orders of magnitude or more, the standard should be prepared by serial dilution from a single stock solution. And that's actually what you'll be doing in lab this week. So in a serial dilution, you start by preparing the most concentrated standard and then dilute a portion of the solution to prepare the next most concentrated standard. And then you would dilute a portion of the second standard to prepare the third to prepare the fourth, and so on until you produce all of your standards. So you'll be doing that this week, and as part of the pre-lab, you'll need to calculate your serial dilutions before you come to lab so that you don't waste lab time doing those calculations. So when you're calibrating the signal for our standard, we do need to try to minimize determinant errors. So determinant errors are just errors that are known and controllable. So they could come from the instrument or personal errors, and you want to try to limit those things. So these should be avoidable errors, right? So we first want to calibrate our equipment and instrumentation. And we do this by measuring the total signal for a standard with a known response of the standard. And then we can adjust the total signal until it's equal to that standard. So for example, we can evaluate a spectrophotometer's accuracy by measuring the absorbance of a very carefully prepared solution of potassium chromate by weighing out 60.06 milligrams per liter in a 0.0050 molar sulfuric acid solution. And then we would use sulfuric acid at that concentration as the reagent blank. So when you measure this solution, if you take the absorbance at 350 nanometers, it should come out at 0.640 plus or minus 0.01 absorbance units. This would indicate that the spectrophotometer's signal is calibrated properly. So for each instrument, you would have a calibration mechanism for being able to tell if the instrument is giving you correct signals within its operating range. Okay, and then the next thing that we need to do is we need to do our standards and standardize the analytical method so that we can determine the sensitivity or the proportionality constant that we're going to need to be able to calculate either the moles of our analyte or the concentration of the analyte within the solution. So we need to use our standard to be able to calculate the K value. So determining K can be challenging. So there's a number of ways that you can do this. We're going to talk about the first two this week, and then we'll talk about a third method next week. So the simplest way to do a standardization is a single point standardization. And this will allow us to calculate that value of K. So in this situation, we're going to have a concentration of the standard that we make up, and then we're going to run it in our spectrophotometer or whatever instrument that we're using to get the signal, and then we'll record that signal. And so if you take that signal and divide it by our known concentration, we can calculate that value for K. And then once we've done that, then we can analyze unknown samples in their sample matrix to try to calculate the concentration in those unknown samples. Right, and the equation for that we just rearranged to be able to solve for the concentration of the analyte. We now have calculated the K value from the standard, and then you can get the signal of your samples to be able to calculate the analyte in there. So this is known as a single point standardization. You have a single standard that you're using to calculate the K value. So there's some downfalls of using just a single point. So if you have any error in your determination of K, it's going to carry over into all of your calculations of the concentrations of analyte in your samples. So they'll all be off, and you may not notice because you only had one standard. So another thing is that the experimental value for Ka is only based on that single concentration of analyte. So we're assuming that it is giving us a linear correlation for all concentrations of the analyte, and that's not necessarily something that we can really assume, right? It may max out in the ability of our instrument to actually measure that. So if we only take 1 point, right, we have one standard and we calculate one signal from that, and then, we assume that it's going to give us a linear relationship, but then our signal for our sample is way past that standard, right? And we come over here and we say, oh, based on our standard, here's what we think the concentration of the analyte in that solution should be. However, in actuality, you may be at the limit of linearity in your sample. Remember, we talked about that in the last chapter. And so at this point here would be our limit of linearity. So anything above that is no longer going to be measured accurately on this curve. But we don't know that if we only do a single point standardization. So it's a little bit dangerous to assume, where you can go on this linear curve with just a single point standardization. All right, so here is a practice question. We will do the answer for this in class. You have a spectrophotometric method for quantitative analysis of lead in blood. And for a standard, it yields 0.474 is the reading for a 1.75 part per billion standard. So what is the concentration then of lead in the sample of blood for which the sample is 0.361. All right, so you first need to use these first two values to calculate your K value, and then you need to rearrange the equation so that you can solve for the concentration of lead. All right, and we will find out the answer when you come to class. Okay, so in addition to having a single point standard, you can do multiple point standardizations, and there's a couple ways that you can do this. We'll be doing this first way in class this week. So a better way then is to prepare a series of standards that contain different concentrations of the analyte, and the standards are chosen such that they bracket the expected range for the analyte's concentration. So a multiple point standardization should include at least 3 standards, although more are preferable, right? You need 3 points to at least get a line, but 3 is not great. You probably want 5 or 6 when you're doing a proper standard at least. And you want to do those in repeat. Replicates of 3 are preferred, but in our class we're going to do 2 replicates per group. And so each person in the group is going to make their own standard curve. You'll read it on the same instrument, and then hopefully they will come out with a high correlation with one another. So you're going to plot your standard curve with the signal on the y-axis and the concentration of your standard on the x-axis. And this will be your calibration curve. We saw a calibration curve in the last chapter. And you're going to be able to determine your limit of linearity. If it's linear through the entire curve that you have, then you know that you can use all the data points in there, but you can't go above your standard, your highest standard, with any of your samples, right? Because you haven't tested out in that range. So you would use your top point as the limit of linearity if you haven't actually reached the point where it's going to curve off and go flat at the top. So some of these advantages to using the multiple point standardization: you can help minimize any determinant error if you make a mistake in one of the standards, right? You'll be able to catch it easier because you'll see, oh, standard 3 was really off in comparison to the other measurements. So I can throw that one out and just use the other 4 or other 5 that's in there. And then because we measured the signal for several concentrations of the analyte, we are no longer assuming that Ka is independent of the analyte's concentration. And we can actually construct our calibration curve and see the actual relationship. So that'll help us determine where our limit of quantification will be and where that limit of linearity will be. So you'll have to make those judgments for your curve and then calculate, the equation for the line, do your linear regression on the correct data points. And so we'll get practice doing that this week in Excel. So the most common method of standardization uses one or more external standards, and that's what you'll be doing this week, each of which contains a known concentration of analyte. And we call these standards external because they're prepared and analyzed separately from the samples. We'll see in the following week, we're going to do another type of standardization where we're actually going to mix our samples with our standards. And so that one is called standard addition method. All right, so our multiple external standards would look something like this. You're going to have blank with just the solvent in there, and then you'll have a very concentrated solution that you're going to use to make each of these subsequent dilutions that have much lower concentrations. And then you go from 0 to the lowest one, back up to the highest one, and you take your signal readings. And you should get a line coming back out. If you reach the top of these spectrophotometer's ability to read the absorbance, which is usually at about 1, you don't want to go higher than 1. Sometimes it can be 0.8. in the reading on your standards on your signal, and that's going to be your limit of linearity for that equation. You can see for this one we haven't reached the limit of linearity, and we may not have reached the lower limit down here as well with the limit of quantification, right? So for this, we would lock our readings in between our lowest and our highest. So when we're analyzing our sample, we're going to want our sample to fall within this range. If it falls lower than this, then we have to be careful when we're making our calculations, because we really don't know where the limit of quantification is going to be for this standard. So if our sample was very dilute and it was less than this, we would probably want to make some more dilutions of our standard just so we could get in the range of where our sample was. And then same thing up here, if we have a sample that's really concentrated and say was reading up at 0.42, our highest sample doesn't go up that high. And so we would want to either make a more concentrated standard so that we would know it's still in the linear range, or we would want to take our sample and we would want to dilute it until it falls into the range of our standard. And then we could take a reading and then calculate the dilution and then back calculate the concentration of the actual sample. Okay? So when you use these multiple external standards, this is called the normal calibration curve. All right, so when you're using multiple standards and you make a calibration curve, you're going to be able to say, okay, here's our limit of linearity, right? And we're going to do a linear regression then along that limit. And then the equation of that line, we can get that, right? And it's going to be y equals mx plus b. And the slope, or the m of our line equation, is going to give the value of k. And this happens, right, when our intercept is actually 0. Right, so that b value would be 0 in this case, and you would get y equals mx. Right? It doesn't always happen that your 0 point is actually at 0. Sometimes it may give some signal, and that just means that the reagent is a component of that signal, and so you'll have to use whatever b value is in there as well. So in this case, if your standard, right, is not a linear equation, but only exists in a linear range for a certain amount of the calibration, then you only want to use the linear component of that curve. So I would have to say, where is my limit of linearity? You know, I might block it here and then say I'm not going to use points higher than that. If my sample is that high, I'm going to have to dilute my sample and then take a reading until it falls in that window of linearity. So our takeaway is that the value of k at any point along our calibration curve is the slope at that point. All right, so we've got a couple of in-class problems. Take a look at both of these, and we will come and visit those in class and work through them together. All right. See you in class.